how can we make use of this cycle in a refrigerator? Now what we see on the left-hand side is your, the refrigerator at your house. There is a compressor, and there are two heat exchangers. One heat exchanger is a condenser, and the other heat exchanger is an evaporator. In order to use that cycle for the refrigeration, evaporator is the key component for the cooling process, right? And now, because we want to cool down the inside of the refrigerator, this evaporator should be inside to be in contact with a certain space that we need to be that needs to be cooled. And or in other words, your condenser should be outside, okay? Because this condenser should dump heat to the environment. So now, after compression process, your working fluid, in that case refrigerant, should go to the condenser, which is exposed to the outside. Then it should go through the expansion device. Then it should go to the evaporator that is installed inside the refrigerator, because that needs to cool down the space inside the refrigerator. Then after take heat away from that space, and this working fluid should go back to the condenser to be compressed again and again. Usually, if you buy a new refrigerator these days, you cannot see the backside. But if you remember, what it looked like from the kind of low, very old refrigerator, like 20 years ago or like 15 years ago, or something like that time, that is what you can see in the backside of the refrigerator. And you can clearly see there are a lot of coils with like thin kind of pipelines, and that is condenser. Okay, so throughout this condenser, heat is rejected from working fluid to the outside. In that case, outside is your kitchen area, and you also can see the compressor that is, kind of in the bottom area of this old refrigerator. So, as a result of running the refrigerator to cool down inside the refrigerator, now we should dump out certain amount of heat. In fact, the amount of heat that we have to dump from the refrigerator should be bigger than the heat that we can take out from the space, to make it cool. Okay? Because there should be a certain amount of work to run this entire cycle. Okay? So in order to make your space cool down, we have to dump more heat to the outside to make the outside space warmer. So there is nothing that you can gain for free. So by running the refrigerator, in order to preserve your food and something else, then you are keeping your kitchen area warm. Okay, same thing can be applied for the air conditioning system. So how it works is exactly the same. If you in the outside of your house, you have that kind of component, right? So that is basically condenser. Okay, so condenser is located outside of your house, and the evaporator should be inside your house. So your evaporator is inside your house, and your condenser is outside your house. And what happens is that in the evaporator, okay, then it takes heat away from your house to make your inside house cool. But more heat should be dumped out to the outside. That sums the amount of heat that is taken out from your house, plus the amount of work that needs to be run the compressor in order to run the entire refrigeration cycle. So in order to cool down your house, in order to cool down your building, in order to cool down whatever you want to cool down, we have to dump more heat to the outside. That would result in more warmer temperature in the outside. So that is always what you have to pay in order to make a certain space to be cooled. In the past slides, we talked about the ideal vapor compression refrigeration cycle, and we tried to draw the TS diagram. But in real field of refrigerator or air conditioning companies, they love to use pH diagram or pressure enthalpy diagram rather than the TS diagram. And now what you see in this slide is an example of pH diagram. And I'm going to talk about why people in that field love to use pH diagram more than the TS diagram. So in order to understand better about it, so let's try to draw one specific vaporation, the vapor compression refrigeration cycle. Here, I'm going to explain, how it looks in the pH diagram. So that is your saturation dome. Then obviously inside your saturation dome, there is saturated liquid vapor mixture. And the left-hand side is a compressed liquid. And the right-hand side is superheated vapor. And all curves that you see in this plot in red colors is a constant temperature curve. So now each curve means that each different temperatures. Okay, so from all the way up to 160 degrees Celsius to all down to minus 20 degrees Celsius. And as you can see, in the saturation liquid vapor mixture, we have horizontal line, and that totally makes sense because in the saturation phase process, your pressure should have the same one saturation temperature or vice versa. So now, with that understanding of the pH diagram, what I'm going to draw is one refrigeration cycle that satisfies condensing temperature at 30 degrees Celsius and evaporation temperature of the working fluid, or R34A, at 0 degrees Celsius. Okay. So now let's try to draw the ideal vapor compression refrigeration cycle, starting at saturated vapor point at 0 degrees Celsius. And where is that point? Where is the state 1? We have the 0 degrees Celsius curve, and this point is the saturated vapor point at 0 degrees Celsius. That should be your point 1. Okay. Now, this working fluid at that point should be compressed ideally to reach its pressure at the pressure of the condenser. So if you ignore any pressure drop inside the condenser, the pressure that we have to compress your working fluid to is the same as the pressure, the saturation pressure at the target temperature of condensation at 30 degrees Celsius. So now at 30 degrees Celsius, we have this much of condensing pressure or saturation pressure, and we have to have that pressure satisfied, which should have almost, it's always kind of horizontal line all the way up to this portion. Okay, so from 1 to 2, we should go up to, in terms of pressure, at this point. And now during the condensation process, it should go to all the way flat, because again, that is constant pressure heat rejection process. And now what happens at process 3, which means throttling expansion process? Again, we should have the same enthalpy before and after expansion process. So in that case, it should be vertical line until it becomes 0 degrees Celsius, which is at the evaporation temperature we target to make. Then from this, we have evaporation process. So from 1 to 2, okay, 2 to 3, and 3 to 4, and 4 to 1. So that is how we can draw the refrigeration cycle in the pH diagram. Okay, how do you feel about this plot? Wouldn't it look simpler than the TS diagram? And also, what matters for that all thermodynamic analysis, which I'm going to talk about in the next slide, is all about, again, enthalpy values at each point. So if you can draw the all points in the pH diagram with given temperature of target and given pressures, then by looking at this plot, we can instantaneously get the values of enthalpy at each point, so that then we can easily calculate the amount of heat and amount of work, from this vapor compression refrigeration cycle. So that is why people in that field of area love to use that pH diagram than the TS diagram. So If we try to do the first law of thermodynamics for an open system, again, the refrigeration cycle, is based on the open system because your working fluid should keep flowing through all components. So if you apply the first law of thermodynamics for an open system under the steady state condition for each component, the result that you can get out of this analysis is exactly the same as what we have done for other open system based thermodynamic analysis. Okay, everything is about enthalpy values. So now, from 1 to 2, okay, which is compression process, your compression, the compression work can be calculated by H2 minus H1. And also from 2 to 3, which is about all condensation process and heat rejection process. And in that case, the amount of heat rejected by the condenser can be calculated by H2 minus H3. And from 3 to 4, there should be no work involved. And we also assume that that is adiabatic condition. So what you can get is that enthalpy at 3 should be same as enthalpy at 4. And the key value, which is the amount of heat addition to the cycle, or the amount of heat that is taken out from the space to be cooled, which is QL, that can be calculated by H1 minus H4. Okay? So by having all enthalpy values of that cycle, we can calculate QL, QH, and WN. And once we find those values out, then we can calculate COP. Again, the COP for the refrigeration can be defined as the amount of heat addition to the cycle divided by WN, or H1 minus H4 divided by H2 minus H1. Or COP for heat pump, then we have to use QH instead of QL. That gives us H2 minus H3 divided by H2 minus H1. However, these are for ideal conditions. Then if you think about the realistic conditions, what kind of realistic factors that we have to consider? Many times, your state 1 is not on the saturated vapor. Many times it is slightly superheated. So that is first real factors. And the second one is that compression process is not ideal, but is irreversible, and sometimes or many times is not adiabatic conditions. And third real aspect is we have to also think about the pressure drop during the condensing process, evaporation process. And also in state 3, okay, after condensation, it's not exactly on the saturated liquid point, but is usually slightly subcooled. So that is another realistic factor that we have to think about.